She will tell us. Anyway, so we actually overlapped at ESO for a few years, and then she's here for the IAU symposium last week. So it's very great to have her and tell us a bit more about what she works on. She just got her PhD a month ago from Tel Aviv University, and now she's a postdoc at Weizmann Institute. So yeah.
Thank you. So thank you, C, for inviting me to give this talk here. So it's pronounced Hallakoun. It's not the way it's written. I just started my postdoc at the Weizmann Institute in Israel. And the work I'm going to show you is basically some of the projects I've been working on during my PhD. And so it was mostly with Dan Moz, who was my PhD supervisor. And I would also like to point C here, who's been collaborating with me on some of these projects. And there are also many other people who contributed. They will be noted in the relevant slides. Okay, so the title of my talk is relatively broad. It's companions and debris around white dwarf. So I'll start by trying to explain you what I'm going to talk about in this talk. Wait, oh. Okay, sorry. So if we take a look at the background photo, we have a picture of the night sky. You can see Orion over here. And if you look here at Sirius and take a closer look, you can see, as you all know, that it's actually not a single star, but a binary consisting of an A-type star and Sirius B over here, which is a white dwarf. So white dwarfs are interesting because they make up more than 97% of all the stars and their lives as white dwarf. And in this talk, I'm not going to talk actually about Sirius-like system, because if you take this system and move it farther apart, you will no longer see the white dwarf, and A star will dominate the spectrum. So what I am going to talk about, I'm going to talk about white dwarfs that on a single look like single stars, but on a closer look might reveal the presence of a binary companion, which could be another white dwarf, or maybe even a planet, or a debris disk, or other kinds of debris that were left by the older planetary system. So I'll start by giving you some quick facts, some quick basic facts on white dwarf that will guide most of the work here. So first of all, white dwarfs are very dense. They have density between 10 to the 4 to 10 to the 7 grams per cubic centimeter. And this immediately tells you that if you look at a white dwarf, because of the high density, all of the heavy elements relatively quickly sink below the atmosphere, and then we have gravitational settling. So here you have some sort of a simplified cartoon version of a white dwarf, where you have a core consisting mainly of carbon and oxygen, on top of it a helium layer, and at the end you have a thin hydrogen layer. Now, most of the white dwarf that we see have a hydrogen-dominated atmosphere. We call them DAs. Now, this classification is based only on how they look like in the optical spectrum. So if we see hydrogen lines, we call them DAs. Now, the second largest group is the DV white dwarf, where we only see helium in the atmosphere of the white dwarf, but they can also have some traces of hydrogen. If we look at the spectrum of a DA hydrogen-dominated white dwarf, it looks like that. This is a spectrum of a DA from the SDSS survey, and you can see that we have a continuum, a black body continuum, and on top of it we have very broad Balmer lines, and that's it. And this is a problem if you want to measure radial velocity for white dwarfs, because you don't have a lot of lines to base your measurement on, and the lines that you do have are very broad, so you can't get really good enough resolution for your radial velocities that you measure. And I'll come back to that later. Another thing you need to know about white dwarf is that they cool as they age. And basically, we can use them as cosmic clocks. If you know the mass of a white dwarf and its chemical composition, you have a one-to-one correspondence between its effective temperature and the cooling age of the white dwarf. That's white dwarf don't produce any more energy, They just start their life very hot and then slowly could cool down over billions of years. Here you can see an example for theoretical cooling tracks for different masses of white dwarf. This is the effective temperature as a function of time. And you can see that if you know the mass and the composition, this is specifically for DA white dwarf with thick hydrogen envelope, you know its age. So I told you that heavy elements sink below the atmosphere of the white dwarf relatively quickly. How quickly? This depends on the composition of the white dwarf atmosphere. So you can see here the theoretical diffusion times for various elements, in red for hydrogen dominated white dwarfs, and in blue for helium dominated, and the different lines are for different heavy elements. And you can see that in this range here of hydrogen dominated white dwarfs that are younger than 300 mega years, the sinking timescales are in the order of days. Okay, this scale here is in years, which means that if we look at a DA hydrogen-dominated white dwarf who's younger than 300 mega years, then we don't expect to see any heavy elements in its atmosphere.
And that's the question. What do you mean by hydrogen-dominated? You just mean the outer layers?
Yeah. When you look at the optical spectrum, you see mostly hydrogen.
And that applies any hydrogen-dominated white dwarf. Doesn't matter what's inside.
Yeah.
Is to the settling time, or are you just talking about the settling time for atmosphere?
Because of the gravitational settling, if there is any hydrogen, usually, at least in this temperature regime, it's concentrated on the outermost layer.
Yes, I understand that, but I mean, are you talking about the time for that little layer to be?
Yeah. So if you take
white dwarf.
No. So if you take a spectrum of the white dwarf, you won't see anything except for hydrogen.
Okay.
So we don't expect to see anything except hydrogen if we look at this range here. However, people did look at this. So, for example, Ben Zuckerman and also Prester et al. And what they find is that between 27 to 50% of DA white dwarf in this temperature range, where we don't expect to see any metals, show traces of heavy metals in their atmosphere. This can only mean, or most likely mean, that there is an ongoing accretion onto the white dwarf, and this is why we see the metals in the atmosphere when we look at them. Otherwise, it would have sink below the atmosphere within days. And when people look, and especially people like C, look at the chemical composition of the heavy elements we see in those white dwarfs' atmosphere, they actually look a lot like things we know from our solar system. So here's a plot from C's paper from 2014. Since then, there have been much more examples over here. You can see here on a plot of the surface gravity and effective temperature, different white dwarf with the chemical abundances of each. And you can see here, for example, the composition of bulk Earth. So green is iron, blue is oxygen. And you can see that we see things that are very similar to things that we see in our own solar system. So basically, white dwarfs eat their old planetary system, and this is our most direct way of measuring the chemical composition of extrasolar bodies. I mean, you don't just do transit spectroscopy and measure only the atmospheric composition of the extrasolar planet, but you can actually see what it is made of in the inside. And this is our most direct way of doing it. Another thing you need to know about white dwarf is that it looks like, if you look at them close enough with good enough precision, most of them are varying. So in the original Kepler mission, which was precise enough, not a lot of white dwarfs were included in the field, but approximately 14 of them were observed with good enough photometry for 4 years. And when Moaz et al., my supervisor, looked at it back in 2015, they saw that approximately half of them, around 7 out of the 14, show this periodic low amplitude variation with periods ranging from hours to days. but the amplitude of these variations is very low. It's between 10 to the -4 to 10 to the -3. So it's very high. You can't really see it from the ground or with a mission which is less sensitive than the original Kepler. The K2 mission was already 1 order of magnitude less sensitive. So there are not a lot of examples of these kinds of variations. So I told you that about 50% of the white dwarf accrete metal from debris, and that about 50% of the white dwarf have periodic optical variability, or at least in this limited sample. So we wanted to test if there is a causal connection between the two phenomena. For example, if we have metal accretion, which is accreted non-uniformly across the white dwarf surface, maybe because of the magnetic field, combined with the white dwarf rotation, maybe if we assume fluorescence, absorption in the UV of the metals, and emission in the optical, we might get this optical variability that we see. And then the period is actually the rotational period of the white dwarf. So we wanted to check this hypothesis. And in order to do so, we applied for a HST time in order to see the metal absorption line in the UV. And we got 10 HST orbits of 7 white dwarfs. So our sample was really small because we didn't have a lot of examples that were observed with the original Kepler. And what we wanted to do to check is to see if we have this periodic variability, do we have this absorption of UV metals in the UV spectrum? And if we don't have the variability, that we don't have these photospheric metals. Here you can see an example of one of these white dwarfs. This is the UV spectrum. This is Lyman alpha. And here you can see some absorption lines, photospheric absorption lines from silicon. The problem is that we couldn't find any significant match, mainly because our sample was so small. But this may not be the end of it, because for 2 things. First, if you look at this plot, this is the chemical abundances of silicon versus carbon, and the black and gray dots are from the Koster sample, the red ones are our sample, and the triangle marks upper limits on the detection. So you can see that the actual detections, the one with the arrow bars, and the upper limits are actually of the same order of magnitude. So it looks like if we have better sensitivity for this metal absorption line, we might detect even more polluted white dwarf that have metal lines with lower abundances. So, and another thing we are considering is that it looks like also that if we have the Kepler sensitivity to observe more like white dwarf with light curves where we can detect low amplitude variations, we might be able to see that actually more also the white dwarfs that seem to be non-variable are varying, and the one that seems to be non-polluter are actually polluted. So we need a larger sample. Now let's move on to some other things you need to know about white dwarf. So some of them show other evidence of planetary debris, except for the photospheric metal line pollution that I already mentioned. About 40 white dwarfs have been observed to have infrared excess from dust disk. So here you can see an example of GD16 from J. Florich's paper. This is the SED that was measured, and you can see that a white dwarf alone cannot reproduce the observed SED. So we need to add a component coming from a warm dust disk. And about 8 more, maybe now 9, I don't remember, white dwarfs show metal emission lines from circumstellar gas. Here you can see an example from Chris Manser's paper of a Doppler tomography map showing where they measure the carbon emission lines coming from the disk over a period of a few years, and they see changes in the radial velocities of these lines, then they can map the structure of the disk while it processes over the years. Now, one white dwarf so far might be the missing link linking all of this together, the photospheric metals, the dust disk, and the circumstellar gas. One dwarf, and this white dwarf is WD 1145 plus 017. It was observed in the Kepler continuation mission, K2, and it showed to have very heavy metal pollution. This is a paper by C. And it has circumstellar gas, this time with absorption, with very wide absorption lines, and a dust disk. And finally, transiting dust clouds coming from a disintegrating asteroid. So what we think that the picture is that we have an extrasolar body, like an asteroid. It disintegrates, emits dust clouds. The dust clouds are the one causing the transit that I will immediately show you. These dust clouds then disintegrates and form the dust disk, which eventually sublimates into the circumstellar gas and finally accretes into the white dwarf as that we see as a metal pollution in the photosphere of the white dwarf. So as I said, it was discovered in K2 data by van der Waal et al. Here you can see the K2 light curve folded over the 6 different periods that they measured. This is the periodogram of this light curve. So you can see that it has multiple transiting objects, all with orbits of about 4.5 to 5 hours, which is within the tidal radius for rocky material around this white dwarf. And when they looked at the transit shape, it looked asymmetric, longer than expected for a solid body, and it was rapidly evolving. All of this indicated that what we are seeing is actually a disintegrating asteroid. So if the transits are caused by dust clouds, maybe if we measure it in multiple bands simultaneously, we will be able to say something about the gas, about the dust composition, because we know that extinction depends on the wavelength to grain size ratio and on the grain composition. So we applied for time using NTT at Isolacea, and we got 6 nights to observe with ultracam, which is a visitor instrument that is currently installed permanently on the NTT. Ultracam is a very cool camera that is capable of taking very fast photometry of faint objects in 3 bands simultaneously. So we went together to Lucia, and unfortunately, on 4 out of the 6 nights, we were not able to observe because of the weather, but still we got these very nice light curves on our first and last nights. So these light curves are only 5 nights apart, and you can immediately see that they are completely different. And highlight here in red are transits of the same object. So this is one period, 4.5 hours, and this is the feature of the same object 5 nights afterwards. And you can already see that 1 cycle later, it already starts to look a bit different. And the ones in blue here are again of the same feature. This is another 4.5 hours. And finally, this one over here is a new feature that appeared out of nowhere somewhere in between these 2 nights. So you can see that the system is very rapidly evolving. And for example, this one here in red, it was much more narrower and deeper on our first night, and it looks like it got longer, the transit takes longer time, and they are also shallower, so it looks like actually a cloud that is disintegrating and taking a larger portion of the orbit. But as I said, we took multiband photometry, and this is what we got when we looked at the different colors. This is, for example, the light curve from our 6th night, and you can see here 3 bands, which is U, G, and I, with the different colors. And you can see, for example, here that the transits look deeper in the redder band than they are in the U band, which means that during the transit we have a higher blue flux. So we got bluing instead of the reddening we were expecting given the dusty environment. So then we had to come up with an explanation for this weird phenomena. And basically what we need is that the transiting clouds need to obscure more of the red flux coming from the white dwarf system than the blue flux. And the way to do so is like this. Remember that I told you that this system has also circumstellar gas. And in this case, it comes in absorption. For example, and this is from C's paper, if you look at this iron 2 line, in black, this is the measurement. We have here a narrow photospheric contribution to the line coming from the metal already accreted onto the white dwarf. And this very wide shoulder, in this case up to 200 kilometers per second, coming from the circumstellar gas. And another thing you need to know is that if you look at the spectrum at different bands, you see that most of the metal lines are concentrated in the UV. So this is the U band versus the R band. All these lines here are actually helium, so they are not metals. And all of these are the metal pollution lines. And when C looked at it in and out of transit, so here are different epochs of the same line. I think it's iron 2, right? In gray is out of transit. In pink, it's during transit. And you can see that during transit, the lines get shallower. So basically, we have less absorption in the UV during transit. And if we can combine all of these together, we can constrain the configuration of the system. So this is what we think is going on. We have a white dwarf, which is rather bluish. And around it, there is circumstellar gas that absorbs more light in the UV. So it makes the white dwarf look redder than it is. And then the transiting cloud comes in and obscures more of the circumstellar gas than it obscures the white dwarf. So basically, when the cloud obscures the white dwarf looks bluer than it is out of transit. And this tells us that the gas and the dust clouds have to share the line of sight, otherwise we won't see this. And that also the gas cover the white dwarf only partially. And this was confirmed recently by C using a very large campaign using HST and in the UV and ground-based observations in the optical, both photometric and spectroscopic. And indeed, we see that during transit, the metal light in the UV gets shallower, and it coincides with the bluing that we observe with ultracam. Okay, so until now I was talking only about debris, but what about whole planets? So until now, no one has found a whole planet orbiting a white dwarf, but we are looking for it. But why is it interesting to find planets around white dwarfs? First of all, if you look at this plot from Eric Agel paper, you can see this is the orbital distance or the orbital period. And until here, it's within the tidal radius of the white dwarf for rocky material, so it's not interesting. And this is the white dwarf age going upwards, or temperature, which I told you is the same. And this shaded area over here indicates the white dwarf habitable zone. So as I said, white dwarf cools down gradually. So it means that the habitable zone actually shifts forward and gets closer into the white dwarf. But still, a planet that stays, for example, here in 0.01 AU can stay inside the habitable zone for a significant amount of time, long enough for interesting processes like evolution to take place. So all of this configuration over here have more than 3 gigayears of habitable zone time for planets in this region here.
But you have to somehow make the water survive before.
Right, but maybe comets can bring them
Okay.
in, because we also see white dwarf polluted with water, with oxygen. Yeah. And another cool thing about planets orbiting white dwarfs is this. If we have a sun-like star and a Jupiter-like planet, then the transit is about 1%. But if it's an Earth-sized planet, the transit is already only 0.01%, while white dwarf is the same size of the Earth. So the transit should be deep. So if there is one, it should be easily detectable, assuming the inclination is correct, and we should be able to do some transit spectroscopy for the nearby white dwarf. And this will be a very good place to look for biomarkers, for example. So I already acquired about 3,800 hours of photometry using the WISE Observatory in Israel and the LCO networks, all smaller telescopes smaller than 1 meter, looking for planets in the habitable zone of nearby cool white dwarfs. I haven't looked into it yet, so this is my next project. So stay tuned. The chances of finding anything are very low. So don't expect much, probably only upper constraints, but it's still interesting to check. Okay, but what about double white dwarf? Double white dwarf are also interesting for a number of reasons. From binary evolution through type 1a supernova progenitor to gravitational wave sources. My main focus is type 1a supernova progenitors. So why type 1a supernova are interesting? First of all, they are important because they are a major source of heavy elements in the universe. And second, we use them as standard candles in order to measure distances, and this is how dark energy was discovered. However, nobody knows exactly what is exploding and how. And this is the so-called type 1a supernova progenitor problem. Now, the main scenario that was popular until about a decade ago was the single degenerate, where we have a binary consisting of a white dwarf and a non-degenerate companion that could be either a main sequence star, a subgiant, a red giant, or a helium star. Then the white dwarf accretes mass from the non-degenerate companion until it exceeds the Chandrasekhar limit and explodes. And this was the popular view until about 10 years ago. But the scenario that has been gaining momentum in the past decade is the double degenerate, where we have two white dwarf, a binary consisting of two white dwarf. They loses energy and angular momentum to gravitational waves, spiral in, merge, and possibly explode as a 1A. However, if the scenario is correct, and this is the main channel to 1A explosions, then there should be enough progenitor systems like this in order to account for the type 1A rate observed in galaxies such as the Milky Way. And this was one of the main claims against the double degenerate scenario, that the rates are not high enough, the merger rates of white dwarf are not high enough to explain the type 1A rate. So we wanted to check this. Another motivation for characterizing the population of double white dwarf in our galaxy is for gravitational wave foreground. Here you can see the gravitational wave characteristic strain based as a function of frequency. Here is LIGO. It's sensitive to a higher frequency over here. And LISA, the future space-based mission, is supposed to be sensitive in this region where we expect to see double white dwarf. And in fact, double white dwarf are going to be the main source of noise, foreground noise for the LISA mission. For example, if we have a 2.7 solar masses double white dwarf with a separation of 0.3 solar radius at a 100 parsecs distance, this would fall here on the characteristics plane plot. So above the LISA threshold. So this system like this could be a verification source for LISA. When they turn on the detection and say that we know about a system like this, if they don't see it, it means that something is wrong in their detection. However, all the farther away systems and smaller, less massive, will consist most of the foreground noise that will limit the LISA sensitivity to other systems. So this is another motivation for characterizing the double white dwarf population. So assume we want to look for double white dwarf. One way to do so is to look at photometric surveys using long base light curves and look for eclipses. This is an example for a an eclipsing double wave dwarf we found in K2 data. But this was only the 6th known at the time. There are a few more known now, especially with CTF. But this is still a very, not very efficient method of looking for double wave dwarf. So we need a more efficient way. And the other way to do it will be to look for radial velocity variation in large spectroscopic sample of white dwarf. They should be multi-epoch. So for each system, we need at least 2 epochs to look for radial velocity variations between the two. And this is what Badenes and Maoz have done back in 2012 using the SDSS survey. They took about 4,000 white dwarf from the SDSS. And in the SDSS, you have, per each spectrum, there are multiple sub-exposures that are used to get rid of cosmic rays. So they utilize these extra exposures per object in order to measure delta RV max, which is the maximal radial velocity variation per each system. And they measure it for the entire system, and they got this distribution. So this is the distribution of delta RV max, and you can see that it has a very wide core, up to 250 kilometers per second. Systems that have delta RV max variation that are within this limit of 250 kilometers per second could either be binaries or single wave dwarf with large measurement error. And this is because the SDSS is not very accurate, and they could only get a resolution of about 80 kilometers per second. However, systems that are in the tail of the distribution over here are very likely to be real double wave dwarfs. So with this method, we can get double wave dwarf candidates, which we can then follow up to actually see if they are real double wave dwarf and solve the system. But before we do the follow-up, we can also compare this observed distribution to a simulated one. And in order to do so, we need to simulate a population of double wave dwarf. How do we do it? First, we draw the white dwarf primary mass, and we do it based on the observed mass distribution of the A wave dwarf, and this is from Kepler's paper from 2015, based on SDSS. Then we need to decide whether it's in a binary or not, which we do based on a parameter we called FP, which is the fraction of all wave dwarf in binaries within a specific separation to which our data is sensitive to. If it is a binary, we need to assign it with a secondary mass, which we draw from a power law with an index beta. But as they saw, the data are not sensitive to this parameter, so we can just choose flat distribution, and it doesn't matter. And then we need to assign it with an initial separation, which we draw from another power law with an index alpha, which is the separation distribution of double wave dwarf at birth, meaning after the last common envelope phase, when the new double wave dwarf emerges from the common envelope, it has a separation, A naught, and it is distributed according to this power law. From here on, we know exactly how the system evolves because it just emits gravitational waves. And after 10 gigayears of evolution, the orbit would shrink, and we know exactly how. Then we need to assign it with an inclination drawn from a distribution, a sinonic distribution. And finally, we get for this specific simulated system, the theoretical radial velocity curve, which we then go on and sample according to a sampling pattern taken from our observed distribution randomly. We assign it with measurement noise, again, based on the observed sample. And finally, we have delta RV max for this distribution, for this simulation. We repeat it for many, many, many more simulated systems, and we get the simulated delta RV max distribution that you can see here in colored line. And the colored line is for different combinations of the parameters Fp and alpha. So the parameters that govern the distribution are Fp, and I remind you that this is the fraction of all white dwarf in binaries within a specific separation. And in the case of the SDSS sample, the separation to which the data are sensitive is 0.05 AU, because we are only sensitive to systems with very high radial velocity shifts, and alpha, which is the index of the power law of the separation distributions of double white dwarf at birth. Then what Carls and Danny did was to compare the observed distribution to many combinations of this F bin here and alpha. And these are the 1 and 2 contour lines that they got. And the solid lines over here are of constant merger rate. And what they found is that the double white dwarf merger rate seems to be of the same order of magnitude of the type 1a rate in the Milky Way. The problem was that because of the very low accuracy of the SDSS data, these numbers were very uncertain. So we needed a better sample. Yeah.
When you say the rate is similar, are you talking about white dwarfs with total mass greater than 1.4?
No, so.
Or you mean all white dwarfs?
Okay, so back in 2012, when they checked it, the super Chandrasekhar scenario was still popular, which is no longer the case. And then they compared both numbers. So the solid lines are, including sub-Chandra system. This is the merger rate for all double white dwarf, and the dashed lines are for only super Chandrasekhar system. And you can see that the super Chandrasekhar merger rate is 1 order of magnitude lower than the sub-Chandra system merger rate. You see that the yellow dashed line is 10 to the minus 14, which is for super Chandra, while the solid lines, the solid red lines, in 10 to the minus 13, which is for including sub-Chandra system. So when we repeated the experiment, as I will show you like in a minute, we already didn't care about whether it's super Chandra or sub-Chandra, because people now believe that most of the type 1a should come from a sub-Chandra, from sub-Chandra systems.
Oh.
You just don't have enough super Chandra, and they also don't really make
say.
a normal 1a. Yeah.
Seems like a very small fraction of the white dwarf pairs would be way less than 10%.
Sorry?
It seems to me like it'd be a very small chance that a double white dwarf system would have that.
Right, right. So we are including, we care about sub-Chandra system. Yeah. It's also, if I'm not mistaken, I think that in simulations, also super Chandrasekhar don't make really normal 1As anymore. Anyway, we needed a more precise sample, which luckily exists, and this is the SPY sample, the ESO-VLT Supernova 1A Progenitor Survey. It was a large program that was carried out almost 20 years ago by Napivotsky et al., and they recently published the final paper using UVs on the VLT. So they got UV spectra, which means high-resolution spectra of about 800 white dwarf, multi-epoch spectra. And using this spectra, we were able to measure the radial velocity with a measurement of about 1 kilometer per second, compared to the 80 kilometer per second you can get from the SDSS. So this is an example for a spectrum, a UV spectrum of a white dwarf from the SPY sample. You can see again the black body continuum and the very broad diagonal lines. But this time, when you zoom on H alpha, you can see that it has this narrow NLTE core, which we can use to measure the radial velocity with this precision. And this is an example for this specific system, where you can see a difference of 130 kilometers per second. And if you remember, in the SDSS sample, anything that has a delta Rabi max of less than 250 kilometers per second was considered single, because we couldn't differentiate it between the two. So we repeated the same experiment using the SPY sample. This time we had only about 400 white dwarfs that passed our quality threshold. So it's 1 order of magnitude less than the size of the SDSS sample that they used. But we had a much better resolution. So this time we were sensitive to much wider system with separations of up to 4 AU. So you can see this is the observed delta R mass distribution that we got. Again, we have this narrow, this core because of the measurement error, but this time it goes only up to 10 kilometers per second compared to the 250 from the SDSS. And all the systems here in the tail of the distribution are double void dwarf candidates. Some of them are already confirmed. So these two surveys, in fact, complement each other, because you see this one only goes up to 250 kilometers per second. And this is because of the size of our sample, which was much smaller, and the systems that SDSS detected are much rarer because they are so close. And this is why the chances of finding these kinds of systems in a much smaller sample are lower. So we combined the constraint we got from both surveys, and this is what we got. So we had to translate the SDSS result to the FBN, the binary fraction of all white dwarf, this time within 4 AU. And this is alpha, which is the index of the power law of the separation distribution of the white dwarf at birth. And here you see the 1 and 2 sigma contours in blue for the SDSS. So you see it doesn't really constrain very well the binary fraction or alpha, but together with the results from SPY survey, which are here in green, we really were able to pin down the location on this alpha F-pin space. And again, these solid lines here are of constant measure rate, and you can see that the white dwarf measure rate that we measure from these two surveys is a few times larger than the type 1a rate in the Milky Way. Now, if we zoom in only on this contour, on the combined contours, what we got is that about 10% of the white dwarfs that look single are in fact double white dwarfs with separations of up to 4 AU, and that the white dwarf measure rate is between 4.5 to 7 times higher than the specific type 1a rate in the Milky Way. It means that regardless, if we don't consider the mass or the masses of these systems, and if they can or cannot make a type 1a explosion, the measure rate seems to be higher than the type 1a rate in the galaxy. Now, what does it mean? It means that if we take the white dwarf measure rate that we measure, 10 to the minus 11 per year per white dwarf, and we multiply it by the galaxy lifetime, 10 to the 10 years, we get that about 10% of the white dwarf we see today are actually have already merged. And if we consider that the type 1a rate is 6 times lower than the white dwarf measure rate, this leads us to the conclusion, assuming that all of the type 1a explosions come from double degenerate system, that about 15% of the double white dwarf measure should lead to a 1a explosion, and that about 10% of the white dwarfs that we see today are in fact merger products that didn't explode as a 1a. One thing to consider is the masses, because these are very uncertain. So for a normal 1a explosion, we need to produce half a solar mass of nickel-56. And you can only do it according to simulations if you have a core density larger than 2 times 10 to the 7 gram per cubic centimeter, which you only have in single white dwarf if their masses is larger than 0.9 solar masses. But we don't see a lot of this in the white dwarf known today. But there is also an observational bias here, because massive white dwarf tend to be fainter because they cool, they undergo crystallization sooner, they cool faster, and they are also smaller. So we actually don't see a lot of them, and it's very hard to see. And also, if they hide in binaries, usually you won't see the massive component, you will only see the lower mass white dwarf because it's much larger and it dominates the spectrum. So there are many places to hide massive white dwarfs, but still it's we need some fraction of the double white dwarf system here to have a secondary massive component which is larger than 0.9 solar masses. So yes?
What did you mean it's larger? I think Isn't the more massive white dwarf smaller?
Yeah. I mean, as the mass second, the photometric secondary is the mass primary. Yeah. So
It's brighter or it's larger?
the massive white dwarf is smaller and fainter.
Okay.
So if you have a binary, usually the less massive white dwarf dominates, and you don't see the other one. Yeah. So anyway, there is a mass discrepancy here that we need to work out, and this is what we are working on now. So we already had 42 hours with users on the DLT in order to follow up all the candidates, double white dwarf candidates that I mentioned from the SPY sample. So this was the first stage of our follow-up, and we requested 50 more hours now. I hope they will approve it so we can actually solve these systems, because until now we only had like a couple of epochs per system. And once we solve them, and here you can see an example from Netherlands et al. Of one of these systems that was already solved back in 2005, then we can get the period distribution and the mass distribution for the primary and the secondary up to a lower limit on the mass. And then we might be able to say something more clever about the possibility of the double degenerate scenario as a type 1A channel. And also SDSS 5, that is planned to start next year, is supposed to get multi-epoch spectra of about 100,000 white dwarf from Gaia, really enlarging our available spectroscopic sample and allowing us to answer much more of this question. And that's it. Thank you. More questions?
I have more, but might want to have a chance.
Well, I have a
Yeah.
question. Granted, my astronomy career started a while ago, so I may be asking a stupid question here, but if type 1 supernovas are actually caused by the merger of these white dwarfs, how confident are we that those are actually going to be standard, consistently luminous events?
You mean, how can we be sure we can use them as standard candles?
Yeah.
Yeah, we can. This is why we check that, because we use them as something so fundamental, but we actually don't know what's causing it. So one of the reasons to understand what is the progenitor system is to understand if there really can be standard candles. Yeah, we don't know.
Okay.
This is why we check it. Yeah.
Is it thought that there's a certain mass range of mergers that produce the supernova 1As? Is any
I know that
constraint on that?
So in simulations, if you have a white dwarf, a double white dwarf where one of the components is like at least 0.9 solar masses, the other one could be very much less massive, and it can still you can still get enough nickel 56 produced in the.
So the sum has to be close to the Chandrasekhar limit. It doesn't have to exceed.
Yeah, it doesn't.
Low
If I remember correctly, in simulations, the super Chandra systems don't make normal 1As. They actually make, I think, subluminous 1As.
But ones that are under the limit can make.
Yeah.
Thought that they make.
Yeah. So actually, the super Chandrasekhar is no longer considered like
Okay.
the
But they
channel
have
for
to
1As.
the ones that are supposed to produce 1As. Is there some close to the limit but not exceeding it, or is it something?
It's not very close, right? It's about 1 solar mass. It's quite far from the Chandrasekhar limit.
Okay, I see.
You have much more you have much more white dwarfs there, but still not. We don't see many of them. So it's still a mystery.
Yes.
Hopefully Gaia and SDSS 5 and all the other surveys will help us to solve this.
My other question had to do with this very high resolution and the fact that there was apparently a sharp core to some of these lines.
Yeah.
How was that produced? Because
So these
generally
are
people have thought that have observed that these lines are very broad.
yeah. So they are usually very broad, but these are non-LTE effects. So you have actually interactions that are not local, and then it's not broad. It's not as broad as the normal lines that you get from the local environment.
Interaction. So
Yeah.
is it would be an interaction between the pair? Or
Higher in the atmosphere, I think, between
higher
the,
in the
yeah.
low pressure. So
Yeah.
at low pressure.
But you don't see it in, this is why, so I said that the SPY observed 800 white dwarfs, and we used only 400 or so of them. It's because in many of them we actually you don't see this core.
I see.
So or the signal to noise ratio is not good
Yes.
enough. So you can't always use this.
A question. What were the you mentioned earlier that you got a bunch of data with the LCO network, and you're going to look for potentially planetary, transiting events. What are the timescales that you were interested in there? I would have thought that those were very short events.
So yeah, so the orbital periods that are considered within the habitable zone are between the tidal radius, which is about 5 hours orbit, to about 24 hours. So beyond 24 hours or so, it's already out of the habitable zone, depending on the white dwarf temperature, of course. But we are interested in cool ones, so meaning that they are old enough, so they should be interesting life-wise. So it's between 5 to 24 hours. But below that, you can also get interesting systems like WD 1145 that I mentioned, the one with the disintegrating asteroid. This is inside the tidal radius, so we should also be able to detect these kinds of systems, assuming that the transits are deep enough, because the precision we have is like a few %. So,
right.
Yeah.
How long would the transits actually last?
So for an Earth-like planet, in this range of orbital periods, it should be around 1 minute.
Right.
The transits of disintegrating objects it can be like 20 minutes, 40 minutes. The 1145 system shows all kinds of
Right.
transit length.
Yeah, that basically answers my question. I use the LCO network a lot, and so was wondering how to get around the readout time.
Yeah. So it dilutes it. Yeah, it dilutes the cadence because it's like like a few tenths of seconds. But the transits should be, longer than 1 minute, around 1 minute, 2 minutes, something like that. So you don't really need very fast photometry.
Right.
Earth-like objects that have survived.
Oh, we don't
In
expect them to
minutes.
survive because
What?
this is within the solar radius, right?
Yes,
Or
but
very
for it
close.
to even gotten to existed for some time, it's got to have survived the red giant phase.
Yeah, so we don't
Spiraled
expect them
in
to
or something?
survive. Maybe, it's a second generation of planet that have formed from the debris, or maybe something that migrated in, or something that was captured. It can be like something from the first generation of the planetary system that hasn't moved, because it would have been inside the red giant, right? So it has to be something new. This is why we're looking at the old white dwarf, so they'll have time for a second generation. Yeah.
All right, now Ma will be here for the rest of the week, so you know where to find her, and let's thank her again. Such a horrible job in pronouncing your name. Let's keep trying. I feel like every time I try hard. Anyway, okay.
Sorry for all the
Yeah.
questions.
Oh, no, it's
I'm Tom Ball.
nice.
I was a graduate student, long graduate Berkeley, and one of the graduate students who followed me, Sarah Beck.
What is wrong?
Oh, yeah, sure.
I'll say hello to her when you go back.
I will. Yeah, she's still there.
Yes.